Hello students. So we have completed 7 lectures in this series of the filter design. This is lecture 7 and this will be the last part of the lecture series. So we have seen that there are 4 kind of FIR filters, that HN is symmetric where N is odd. The second is HN symmetric where N is even. Third is HN is antisymmetric, N is odd, and the fourth is Hn is antisymmetric, N is even. So these are the 4 conditions of the FIR filters. We have seen that in the previous part. Now in this part we will be looking at the frequency response of these 4 cases. A very simple kind of question can be asked. So how to tackle that question we will be looking in this lecture. Frequency response of the linear phase FIR filter. So let us take the case 1. Okay, so let us take case 1. Case 1 is Hn is symmetric and N is odd. So the best way to solve such question is take an example. So let us take N is equal to 3, a very simple example, the simplest example that can be possible. So N is odd, so Hn will be H0, H1 and H2. Okay, only 3 values will be there, non-zero values will be there, and it will be symmetric about N equals to 3 minus 1 divided by 2, that is 1. So I can say that H0, or I can say that Hn is equal to H of 2 minus N. So H0 is equals to H2. Okay. Now if I write H e to power j sigma, then it will be equal to H0 e to power j0, H1 e to power minus j sigma, H2 e to power minus j2 sigma. Okay. Now since H0 and this term is equal, so taking e to power minus j sigma common from the whole term, we will get H0 e to power plus j sigma, H1 plus H2 e to power minus j sigma. So these two terms in H0 and H2 are equal, so they will form a cos term. So e to power minus j sigma 2 times of H0 cos sigma plus H1 is the H e to power j sigma. Now we can easily say that this is the magnitude part of the H e to power j sigma, and this is the phase part of the H e to power j sigma. So I can say that magnitude of H e to power j sigma is equal to 2H0 cos of sigma plus H1, and phase is equal to minus sigma. So this we can see clearly. Now this is the magnitude, and we can see that it is a linear phase. Okay, so there's a linear phase. Now if we look at the magnitude, then magnitude H e to power j sigma will be equal to, as we can see, plus 2 times of H0 cos of sigma. Now we can see that this function will be a even function. Okay, will be a even function, and if I plot this, then the plot will be on the sigma axis going from 0 to 2 pi. So it will be h1 plus 2h0, and at 2 pi also this will be h1 plus 2h0. At pi it will be h1 minus 2h0. So the plot will be something like this. Something like this. So it will be symmetric about pi. So the plot, the magnitude plot will be symmetric about pi. So this is an important conclusion. Magnitude plot will be symmetric about magnitude plot. Okay. Now this conclusion is valid for all, because here I have copied from a book. Here n is equal to 9, and here also it is symmetric about pi. So this is the symmetric line, and this is pi point, and this is 2 pi point. So the magnitude plot is symmetric about pi is a conclusion of this FIR filter, where Hn is symmetric and n is odd. Okay, so this finishes case 1. Now let's move on to case 2, where Hn is symmetric and n is even. Okay, so let us take a simplest example. Let n is equal to 2, and since it is symmetric, so h0, or the formula will be Hn is equal to capital N minus 1 minus n. This implies Hn is equal to h 1 minus n. This implies h0 is equal to h1. Okay, now since n is 2, so Hn has only two non-zero values, that is h0 and h1 only. Only non-zero terms. Okay, so hz, so these are actually the examples I am taking, so that the examples are very simple and we can easily get to the conclusion without any problem. So h e to power j sigma will be equal to n equal to 0 to 1 hn e to power minus j sigma n, that is h0 plus h1 e to power minus j sigma. Since both these terms are equal, so it will come out to be 2 times h0. Sorry. Since both these terms are equal, first of all let's take common e to power minus j sigma by 2, h0 e to power plus j sigma by 2. Okay, now this will give me a cos term, so e to power minus j sigma by 2, 2 times h0 cos of sigma by 2. Okay, so we can see that this is the magnitude and this will give me the phase. So the magnitude is equal to 2 times h0, where h0 is a constant, cos of sigma by 2, and phase is minus sigma by 2. Now if I plot the magnitude with respect to sigma, then 0, 2 pi and pi is here. So At 0 it will be 2h0. At 2 pi it will be minus 2h0, as we can see, and the plot will be at pi, the magnitude will be 0 because it will be cos of pi by 2. So the plot will be something like this. Okay, so I can say that the magnitude response is antisymmetric with respect to pi. So the magnitude response is antisymmetric with respect to pi. Okay, so this conclusion is valid for bigger values of n also, because here I have copied the magnitude plot for n equals to 8, and here also we can see that the magnitude plot is antisymmetric with respect to pi. Thus this is the conclusion for Hn, where Hn is symmetric and n is even. So this is valid. So this conclusion is valid for bigger values of n also. So now let's move on to case 3. Where Hn was antisymmetric and n is even. Sorry, n is odd. So Hn is equal to minus times of h capital N minus 1 minus n. So let us take n is equal to 3. Okay, so there are only 3 terms, h0, h1 and h2. Okay, so Hn will be equal to h of 2 minus n. So h is so minus times h0 equals to minus of h2, h1 equals to minus of h1. So from here we can see that h1 has to be 0. Okay, so Hn has only 2 terms left, that is h0, 0 and h2. Okay, and h0 equals to minus times of h2. We have seen this. Now h e to power j sigma will be equal to h0 plus h2 e to power minus j 2 sigma. Okay, because h1 is 0, right? Now since these two are opposite to each other, so I can write it as h0 minus h0 e to power minus j 2 sigma. Taking e to power minus j sigma as common, so we get h0 e to power plus j sigma minus h0 e to power minus j sigma. Okay, now we can see that this will make a sine term. So e to power minus j sigma 2j sine of sigma whole multiplied by h0. So e to power minus j sigma e to power j pi by 2 times h0 sine of sigma. So we can see that this is the magnitude part and this will give me the phase part of h e to power j sigma. So we can say that the magnitude is 2 times h0 sine of sigma and the phase is minus sigma plus pi by 2. Okay, now if I plot the magnitude with respect to sigma, then I'm only plotting the magnitude. Okay, 0, pi and 2 pi. Okay, so if I plot the magnitude, then we can see that the magnitude will be at 0 it is 0, At 2 pi it is 0, at pi also it is 0, at pi by 2 it will be maximum because it's a simple sine curve, right? At 3 pi by 2 it will be negative maximum. So the plot will be like this. And the maximum value will be 2h0 and the minimum value will be minus 2h0. Okay, so we can say that the magnitude plot is anti-symmetric magnitude plot, and it is anti-symmetric about sigma is equals to pi. Okay, now this result is valid for bigger values of n also, because here you can see the result for n is equals to 9. Here also the magnitude plot is anti-symmetric. Okay, so we can say that when Hn is anti-symmetric and n is odd, then magnitude plot is also anti-symmetric with respect to pi. So this is the conclusion for case 3. Now let's look at case 4, the last case, where Hn is anti-symmetric and n is even. Okay, so let us take n is equal to 2. So Hn will be equal to minus times of h of capital N minus 1 minus n. Hn is equals to minus times of h of 1 minus n. So now since n is equals to 2, so Hn will be non-zero at h0, or will be non-zero only at two values, that is h0 and h1 will be present in Hn only. So h0 will be equals to minus times of h1 from the above property, that is Hn is antisymmetric. Now if I write h e to power j sigma, that will be equal to h0 plus h1 e to power minus j sigma. Now taking e to power minus j sigma by 2 common, I will get h0 e to power plus j sigma by 2 h1 e to power minus j. Okay, sigma by 2. Now since these two terms are opposite to each other, so I can write it as h0 e to power plus j sigma by 2 minus h0 e to power minus j sigma by 2. This will make a sine term and we will get 2j into h0 sine of sigma by 2. So this will give me, because j can be written as e to power j pi by 2, 2 times h0 sine of sigma by 2. Now this is the magnitude part and this is the phase part. So I can say that magnitude e to power j sigma is equal to 2h0 sine of sigma by 2, and phase will be minus sigma by 2 plus pi by 2. Okay, now if I draw the magnitude of the function of the system 0 to 2 pi, okay, now we can see that the plot will be 0 at, so the plot will be 0 at 0, it will be 0 at 2 pi, but it will be maximum at pi, because when we put pi in this equation it will become pi by 2. So the equation will be like this. sorry, the plot will be like this. Okay, and the maximum value will be 2h0. So we can say that here the magnitude plot is symmetric about pi. Magnitude plot is symmetric about pi. So this result is valid for bigger values of n also, because here I have copied for n is equal to 8 and the result is same. So we have, in this lecture we have seen for all the 4 cases of FIR filter how the filter response will be. Okay, so thank you. Keep sharing these lectures, and this is the last part of the lecture series. Keep sharing these lectures and give us your feedback. Thank you.